Hi, this video describes states and state spaces. What are states? Well, states are quantities that describe a system. Now, when you're doing mathematical modeling, typically you're trying to describe things that are changing in time. That's why we're so used to seeing these types of graphs where time is the independent variable on the horizontal axis and the dependent variables, the states, are located on the vertical axis. That's because each and every state is itself a function of time. In mathematical modeling, time is the independent variable and the states are the dependent or output variables. Have you ever wished that there was a place that you could just throw all your dependents no matter what time it was? Tee. Well, now you do. That's called the state space. You see, state spaces display the states or dependent variables only. Time still exists because time is always the independent variable. All the states are changing in time. But in a state space, time is implicit rather than explicit. Here on the time series graph, time is explicitly seen on the graph. Now in a state space, because we only seek to display the output or dependent variables, time is going to be implicitly in the mix. Time is going to trace out curves in the state space. You can see that I've given 3 different examples of state spaces, 1, 2, and 3 dimensions, and we'll see how this plays in with an example. Now let's say that we start with a one-dimensional system where we're just seeking to describe one quantity as it changes in time. In terms of ecology, maybe we have a population of alligators. So let's call that population of alligators A of t, and let's mark that on the time series graph. Let's say our population of alligators, A, which is technically a function of time, is going to be growing over time. So our population of alligators is increasing in time. In terms of its display in a state space, we would call this a one-dimensional state space because so far the only output variable we have is A of t. Now A of t seems to start at a small quantity, and as time increases, it gets larger and larger and larger, and on a state space graph, that would simply look like a green dot moving to the right in time, because to the right means an increase. Really, as I'm moving this dot to the right in time here, you want to think about that as corresponding to the output variable getting higher and higher and higher over time. Okay, that's pretty simple, but just to make sure you understand, time is not actually explicitly displayed on this graph. Each one of these points is describing the state of the same variable, number of alligators, but at different points of time. So you can see that this might be time 0, time 1, time 2, etc. Okay, let's start to make things a little more complicated. Let's say that we have our population of alligators, and then all of a sudden another species comes into the mix. Maybe that species is a group of octopuses. Alligators and octopuses, a classic tale of brains versus brawn. So now we have 2 output variables, which would lead us to a 2-dimensional state space. Going back to the time series graph, I'm going to make a display of the octopus population as it changes over time on the same graph that I'm describing the alligator population. Let's say that we started with a lot of octopuses, but over time, the amount of octopuses we had went down. I wonder why. The amount of alligators went up. Maybe there's a little interaction. We'll talk about that more later. But for now, let's practice going from this description of both of those things changing in time to a state space where time is still in the mix, but it's not explicitly written into the state space. So since we have 2 output variables now, we have a 2-dimensional state space. And here in the 2-dimensional state space, we're going to mark one of the axes as one of the dependent variables. Let's say that the horizontal axis corresponds to alligators, and then we're going to mark another axis as the other dependent variable, and so I'll put O for octopuses on the vertical axis. Okay, so at this point we really have to make sure that when we're looking at a 2-dimensional graph, we're differentiating between two output variables that are both changing in time and their corresponding description in their state space, versus a graph like this, where the horizontal axis is always describing time, because really, underneath it all, these things are always changing in time. Remember, state spaces are displaying the dependent variables only. So if we had this situation, where both of the octopuses and alligators are both moving in time, what would that look like over here in the corresponding two-dimensional state space of octopuses and alligators? Well, as we said before, the alligators were kind of growing in time, so the alligators were getting bigger over here, and the octopuses started at a high amount, but they're kind of shrinking in time. And so we're going to end up describing things in the state space as an XY point, where really we have alligators followed by octopuses. So it's going to have an X component, and that represents one of our output variables, and then it's going to have a Y component, and that's displaying our other output variable. How does something like this look on a state space like this? Well, alligators are starting small, and octopuses are starting high. So we're starting somewhere up here. And then over time, the amount of alligators is going up, which means that on the alligator axis, I'll be going to the right, but the amount of octopuses is going down. And so on the y-axis, I'll be going down. So it turns out in the two-dimensional state space description, you're going to see a curve that looks kind of like this. Let's kick it up one more notch, because that's about all we have the ability to visualize as humans. So let's put one more dimension into play, and let's say that, well, this is an underwater example, so we've also got some fish swimming around, right? And so let's say that we also seek to model the fish population in time, and maybe that fish population is pretty steady, holding steady there where I have this pretty much the same amount of fish for all the different time points. Now, if I also want to get the dependent variable of fish as a function of time onto the state space display, now I've added another variable. And so instead of just having the two-dimensional XY point here, now I'm going to end up having 3 dimensions. I'm going to have alligators as my first dimension on the horizontal axis there. I'm going to have octopuses as my second dimension, located on the vertical axis there. And then for 3-dimensional space, I'm going to end up having fish as my third dimension, and that would be the dimension that's kind of coming out of the board. This is really a 2-dimensional representation of a 3-dimensional space. If I actually wanted to represent it in 3 dimensions, the f-axis would really be perpendicular to the board, coming right out of the board. Okay? Let's again see how the curve would play out in the state space, keeping in mind that time is always there. It's just not explicitly written in. It's kind of implicitly allowing us to trace out curves in this space. Okay? And so remember, we started with a lot of octopuses, a little bit of alligators, and a medium amount of fish. So this is a little bit hard to draw on a plane, but I want you to try to think about it as a 3-dimensional space where I've got a lot of these, some of those, and a medium amount of those, and I've kind of got something that looks like this, let's say. See, the fish is in the middle, the octopus is high, and the alligators are low. Geez, I wish I could really draw it in actual 3 dimensions, but I'm doing the best I can. Okay. So that's the representation at a single time point of the 3-dimensional space that has 3 different species interacting. And then, as we travel through time, remember time's always the independent variable, this point is going to move in space. And you're going to remember the octopuses are going down, the alligators are going up, and really we're kind of in this plane where the fishes are staying constant. And so we have some sort of 3-dimensional curve that's getting traced out in the space.